Hello everyone, my name is Alexander, and as you may have guessed, I'm going to tell a story and on what I learned about interaction with database when more than one connection is involved. When we build something that is like 15-minute blog application where all users are isolated, they create posts, likes, comments, we will not see most of what I'm going to show you today. But when it comes to user collaborating on single resource or updating shared resource, collaborating on something or sharing resource, it's a completely different story. But before we get into that, here is a short story about what never happened to me in Asia. So last year, when I was working for a company based in Europe, I traveled to their office. Coming to Europe after spending a few years in Asia was definitely an interesting experience. I thought I was able to finally see the beauty of Europe for the first time, like after living there for many years, actually. Good times. I wanted to visit another country on the way back, so I came to airport to check in. Gave my passport to a lady on the check-in counter. She checked the details and said, "You get a standby ticket." And I was like, "Standby ticket? Do I stand by my seat then?" "No," she said, "you stand at your gate and hope you will have a seat." Interesting, I thought. Like, at that time, I just finished reading a famous book called How to Win Friends and Influence People, and guess what? It didn't help me even a little bit. Neither I made friends with that lady, nor I was able to influence her to give me a seat on the flight. But I thought this could be a talk for a Ruby conference. So we pretend it's not overbooking when airline sells more tickets than aircraft can carry, but something more interesting. So here is an applications we are going to look at today. It has passengers, flight seats, flight tickets, payments, and booking statistics. And flight seats belongs to passenger, can be available, booked or checked in, and flight tickets just belongs to passenger and flight seat. Here is models, as you may see, passenger, flight seat, and flight ticket with a validation. We are not supposed to issue a ticket if seat is already booked, right? Now imagine we have a new code party announced, like same as yesterday by one and only Casa. By the way, you have to know Casa. Casa, you have to know it was absolutely amazing. Thank you. So, two people, Alice and Bob, who missed the party yesterday, really want to come and be a part of it. So they would need to travel, and the only thing, and there is just one seat left on a flight. They hurry up, booking tickets almost instantaneously. The app gets the first available seats. They issue a ticket and update a seat. But then something unexpected happens. We issue two tickets instead, and the only seat that was available belongs to Bob. Let's look at the code again. Isn't validation supposed to prevent this kind of problem? Or the guard clause that we have, but in the end we still issued two tickets, and even Alice was the fastest. It's the Bob who goes to the party. So two people, two parallel requests, both load the same available seat from a database, and it's still available at the time of request. And then it being passed to the flight ticket model where validation happens. Validation checks the loaded record, it says it's still available, and then proceed. So it updates the seed. The first idea that I had when I was looking at it is that we can make it more reliable. We check against value stored in database, not against the loaded value that we have in memory on the application side. So we make a change. Instead of checking attribute, you'll go to a database. We also make sure that Alice, who first books the tickets, gets the seat. So we try again. We can now see new queries that originates from validation. We can see that validation in flight ticket works, and only one ticket is being created, but seats still being assigned to Bob. It happens because issuing tickets and updating seats in this application is two separate operations. So it's time to introduce transactions. So this is the characteristics of transactions in database. The A stands for atomicity, which means that a transaction is treated as a single unit. So if we have more than one operations in it, they either both would be present in a database after it commits, or it would roll back. It would roll back completely. The consistency means the transaction transform database from one valid state to another. This could be the valid state from a database schema perspective or valid state from application perspective, not the valid state from a perspective of what we think it could be. Isolation means that two concurrent transactions do not interfere with each other. And durability is once it's committed, it's committed. Well, unless something completely unexpected happens, like storage damage or something like that. So at this moment, we need atomicity here. So instead of two separate operations that we have, we introduce a transaction to wrap it as a single operation. So we try it again. We see that two transactions begin. First transaction commits. Second transaction checks the seat status in database. Nothing related to issuing tickets. No queries, as you may see, but it's still getting updated. Looking at the code, you can see that we use create and update without exclamation mark, and Rails will only roll back transaction if exception has happened inside it, and create and update without exclamation mark simply silently return false. So let's fix this and replace it with their counterparts with exclamation mark. We try again. We see two transactions begin. One commits, the other check for a seat. Validation fails. In this case, exception is thrown, and the whole transaction is rolled back. So yes, Alice goes to quad party. She gets the ticket and gets the seat. But now, ever wondered why this condition is not triggered? So that's because both transactions see this seat as available when it starts, and we can fix it by marking it unavailable on the database side. So we add a lock method, and it will slightly change a query. It adds for update, and for update puts a lock on selected row. At every single moment in time, there could be only one transaction having for update lock on a specific row. There are actually more type of locks. You can see it here. Two most commonly used are for update and for share. So in simple words, there could be many transactions at the same time having a lock for share, and if any lock for share exists, any attempt to lock for update will have to wait until it's released. So basically for share, it will ensure data to be the same throughout transaction if we need to read it multiple times, preventing any updates to it. So back to our transactions. We see that first one begins, acquire lock, do its business, and commits. The second one, though, had to wait. It sees no available seats since we only had one and returns early. It makes perfect sense to make other transactions wait for this one to complete. But if we have more than one seat available, we can let other transactions to lock other seats for processing and not to wait for this one. So we add one more seat for our test case. We also add skip locked, and now we should be able to have more than one seat. More than one transaction run in parallel. So two begin at the same time, as you may see. They don't wait for each other and lock different seats, as you may see here. So both get different seats, proceed with issuing tickets and commits. No wait this time. So we get this sorted out. Time to pay for a ticket. Alice is eager to make a payment, hitting the submit button 10 times per second. And what could go wrong? You guessed it right. Double payment. So since we first go to payment gate to deduct amount and then we save data to database, unique index will not help us here. There is a special kind of locks in Postgres that help to deal with this kind of situation. It's called advisory lock. So we use Postgres PG advisory exact locks here that automatically released when transaction completes. But there is also PG advisory lock, the one without exact. It gives you manual control. You need to manually acquire it and manually release. There is also locks for shared access and exclusive access. Here we use exclusive lock since we are going to update some data. We run the code. We see two transactions. Both try to acquire advisory lock. One fails and exits, and the other one proceeds, interacts with third party and commits. Exactly what we expect it to be. So our application was working really good in production. Management come for new requirements. They want to make it better for from user perspective, and the management want to see 2-day bookings, like live dashboard. So, and then we ran promotion, got more bookings, and with the bookings, lock timeouts. So anything looks suspicious to you here? So this code sent email synchronously inside transaction, making it way longer. And this transaction updates shared resource and put a lock on it implicitly without us explicitly writing lock. By shared resource I mean that single row in booking statistics where we update a counter. And then since we send email after we updated the counter, the transaction would need to wait until the email is sent. So we see many parallel requests started in transaction, and we see that it started email sending for a passenger on the top. So I have to make one note here, is by default Postgres will make transaction wait for lock indefinitely, but it is generally a good idea to have some limit. Like the same thing as if you send HTTP request, it's generally good idea to have a timeout for it. And as you may see, we have a lock timeout here because transactions that we are waiting for a lock on booking statistics waited for too long. And yes, I know you can move counter to Redis. It works for non-critical counters though, because you can easily violate this consistency part. Let's say let's say the transaction was rolled back, but we incremented the counter in Redis, or the transaction commits, but we somehow failed to increment counter in Redis. And one day you will need a counter that is consistent. And the answer for the ultimate question of life, universe, and everything is 42. No, joking. Slotted counter pattern. So instead of one row in database, we can have many. And we, like, let's say for 100 requests, we would have like 25 rows, and we randomly pick a slot to increment. That way we have not a single shared resource, but many, basically eliminating this problem. And yeah, there is a gem for it from Able Martians. There is another side of a problem here, though, is having HTTP request inside transaction is generally a bad idea. And common way to address it is to move it to background job, right? So we learned the lesson, made the changes, rerun the code, and what we see, most emails sent successfully, but some are not, saying it couldn't find a ticket. And this one problem could be really hard to debug, or one of the hardest things to debug for you, because sometimes job processors pick up job immediately, sometimes there is a slight delay in it, and it will look like it mostly work. It will work always if you put a breakpoint on it, or like, and if you retry, it will work as well, for sure. And success or not will depend on if transaction were fast enough to commit before job picks up, before job queries information from database, or if transaction is still in progress, new information will not be available outside of transaction. And even solid queue is not an option here, since the recommended way for solid queue is to have a separate Postgres database for jobs. And this is also the reason, if you try to debug tests using transactional fixtures, that you didn't see any data in the database. That's because the test wrapped in transaction, and when test starts, you cannot see data outside of transaction. So solution to this problem is well known. You just queue your job after transaction commits, and if you use callbacks for it, just use after commit, not after save. Okay, switching topics now. So we get the seed, had a reason to call support, and had a nice conversation with them. Then you go to put some notes and on your tickets that you express your will to have emergency seat exit, and then the employee having a pleasure having a conversation with you also want to put some notes saying that treat this gentleman with a dessert, let's say. All good intentions leading to a lost update. Can we make an employee to see our update before she made her update? This is where there is something in Rails for it. It's called optimistic locking. It is optimistic because we optimistically assume minimum conflicts. So to enable it, we add lock version column and then pass it around with every response request cycle as a hidden field. And if it is different, Rails will reject changes with stale object error. In this case, we make sure the other user see what actually happened, see the updated information before saving their changes. Okay, imagine this future airlines allows you to swap seats. You see your friend on the same flight, you ask a person to sit next to it to swap seats. So you open an app, choose each other, both click submit, app starts to process the request, and then it happened. A deadlock. It's actually not as scary as it sounds. No one would die out of it. In simple words, this is when waiting for a log to be acquired, simply waiting will not help. Is our first transaction acquired log for a seed 1 and tries to acquire for a log for a seed 2, and the second transaction gets a log for a seed 2 first and tries to acquire a log for a seed 1. So because it cannot be resolved by simply waiting, Postgres will terminate one of those, one of the transactions. And the solution to it is, if you have multiple resources that need to be locked for the transaction to complete, is to lock it for in the same order. So in our case, we sort the seeds and then we try to update it in the same order. This also applicable when you need to update multiple tables as well. It's not only the single rows in the same table. And after doing this, it works without issues. So that is it for this talk. I covered basics of transactions, pessimistic and optimistic locking patterns, and what can happen when you start using them. So next time you work on an application that allows two users to collaborate on something, you all know what to do. Thank you.
Thank you, Alex. Are there any questions?
Did you get on the flight?
Yes.
I have a question. Oh, I could just ask it. Right. That was a great talk, and I really enjoyed how you characterized the various issues that can occur. And it just made me think, I wonder how many code, like how much code out there is broken. How much code must be in the wild that just doesn't use transactions properly, or like just doesn't work properly in these edge cases. And it's kind of scary to think, like, have you thought about it? Like, how many applications have you worked on where you think, oh, we need to have a lock here, or we need to have a transaction here? And
On my past project, the couple of scenarios I get from my past project is one of the scenarios I get from my past project is when I didn't really know that the HTTP request is happening inside the transaction, so I benchmarked everything, making sure that on that high load, if I update a single counter from 1,000 parallel connections, it would work fine until I deployed it to production and then started to get in log timeouts. And then I was like, why?
yeah.
And there is also a gem from Evil Martians to detect HTTP requests inside the transactions. So I don't really remember the name of it actually. Huh? Isolator. Yes, yes.
Thank you.
Other question?
Thank you for the talk. I see you use thread in the test to simulate the scenario. Is that do you actually write tests for all or some of the scenario in the test suite? I see you use threads to simulate the scenario. I'm curious, in the real project, do you also use a similar strategy in your test suite? No, just testing. Oh, okay.
But for a production code, yes, there was a scenarios when we need to use threads and mutex to control the execution, but not in tests.
Okay. So, if there's no question, we will go to lunch. lunchtime. So afternoon session will start from 1:30 p.m.
Yeah. For speakers and the staffs, we have bento and bubble tea. Yeah. Please get your bento and bubble tea here.